Okay, let me start. Yes. See, last time I made there's a correction that I have to make. Okay, so I guess it was Paramalai. I don't know if Paramalai was who suggested that an SCC, a strongly connected component, what we should be looking for is maximal. I mean, I did my definition. I got a bit sidetracked, and the SCC, that the strongly connected component that we should be considering are maximal. And I guess it is Paramalai, correct, Paramalai? You are the one who noticed that. So yes, what we should be, as a matter of fact, standard SCC itself is defined in most definition as a maximal SCC, and that's what we should be identifying the penalty. So that's one correction. It's just that the non-triviality is added as an additional and non-trivial. So like Paramalai pointed out, we are looking at maximal. By maximal means that it will it should not have no other C prime which includes this. If it includes, then it has to be bigger. So, and it's non-trivial if it contains at least two nodes. Okay, sometimes the standard definition, even a single node subgraph can be an SCC because everything else is connected to everything else. But here, non-trivial means a single node will be considered as an SCC only if it has a self loop. Okay, and that is the definition. Why is it significant for us? It represents it, as you know, it represents an island of, a subgraph island inside the graph for M that contains one or more interconnected cycles. And cycles are important for us because we are looking to identify infinite paths in finite state transition system. And those can be, in a finite state transition system, paths can be infinite only if, after a point, something repeats infinitely often. And that can happen only if it is, in a finite state system, if it is part of a strongly connected component. Okay? So every infinite path, then it'll have a finite prefix followed by pi1, where every state, followed by an infinite suffix, where every state in pi1 itself, is part of some non-trivial maximal is strongly connected component, so that they are formed, those infinite suffixes created out of traversals of cycles, various possible cycles that get formed inside an SCC. Now, so our starting point in this algorithm, especially for the case where you have to check EG like property, will be SCC. But a small aside that I want to make, and this is while describing this, is what I got sidetracked and a bit confused. So here, what I want to do is see every such path in an infinite state system has this kind of a form, okay, where you have some finite part. Every infinite path belong to this kind of a language, okay, where pi1 0, the one that the finite suffix belongs to some recursive expression, okay, so a recursive expression, and you have the part that gets repeated will itself have to be some word inside a representable as a finite expression. So any path, infinite path in a finite rate transition system is representable in this fashion. So this is an aside. Now I don't know if you. So I'll give you an example. Okay, this will be clear. and this is not important to the algorithm. So I'm just taking a side tour, okay? So to show what the structure or the set of parts generated, finite parts generated from a finite state transition system, the patterns would be like, and SCCs play an important role. For example, take this graph of a transition system into .com. So what are the infinite parts? The set of all infinite parts that you can generate from this. For example, here you can start from S naught. So this one has two maximal strongly connected components. Correct? There is S1, S2. This one that includes S1, S2. The other one with the self loop in S3. Therefore, so the infinite parts, the set of all infinite parts that can be generated can be represented, as I told you in this footnote, in this fashion. So you start from S naught, and then you could, keep circulating ad infinitum inside this the first strongly connected component that contains S1 and S2. Or you can have start from S naught, and then you could traverse the cycles inside the first SCC a finite number of times, after which you end up in S3 and you stay there forever. So these are the only two kinds of classes. So you see, that is why. So every such, the entire set of all things can be represented in this in this fashion. Okay, so you're are you with me? Okay.
Yes, sir.
Yeah.
Yes.
So yeah. Okay. Good. So suppose you had another self loop in S2. Okay. Suppose, okay, there was a self loop in S2. Then you still have two strongly connected components, maximal strongly connected components. One is the self loop with S3. The other one, since we're picking the maximal thing, so it'll have this loop formed by S1, S2, as well as the self loop in S2. Now, you see, then also if you look at it, so then the pi1 part can be represented as all possible ways in which you could cycle inside that maximal SCC formed by the nodes S1 and S2. So then you will have one set of infinite parts generated that is generated by just being inside S1, S2. Okay, and that's what. So there are things you could generate. Okay, so you can either alternate, okay, between S1, S2, the cycle formed by S1, S2, or the self loop formed by S2, okay? And that's what the third one here gives you. Okay, so there you're alternating between a finite number of times in the first cycle, and then a finite number of times in the second cycle, which is the self loop. And you can go back and back and forth. Or you could alternate between those two loops, a finite number of times, 0 more times, and then you can end up inside S1, S2. Or you could alternate between these two subloops that are there in that SCC. And then you can end up in, S2. See, so all these blue ones, they are formed by a part of the first strongly connected component. Okay, the second one is, the infinite part is formed by the second strongly component, and that's how all patterns can. All the set of all infinite paths can be structured. So in general, it can be a bunch of these kinds of things where every the pi11, the regular expression inside pi11, is part of some part of some strongly connected component as a maximal strongly connected component. Okay, so that's how it will be. See, this is kind of an aside. So that's why for the purpose of this algorithm, if you want to check EG-like property, you have to identify strongly connected. Just identify strongly connected components are good enough. If you want to investigate analyze infinite paths. Okay, so this kind of thing we can. I don't know if you guys are taking any other course on automata-based verification. Are you taking? I know Ratnakar is taking it. Are you guys taking that as well?
No, sir. We are
No, sir.
Okay. So then see there, we will, when we discuss, see, there are lots of other courses here at CMI which deal with automata-based verification. Sometimes that's why I've made this course a little bit more focused on symbolic verification. But assuming that I find the time, I will briefly touch upon this automata-based verification. Okay, so now this kind of language for specifying infinite paths is called omega regular languages. Okay, so where so the set of infinite words are extension of regular languages to infinite word languages that describe infinite words. So there, every the language is expressed by infinite words of this fashion. It's a union of these kinds of things where pi10, these pi's are drawn from regular expressions. Okay, and you can see that. So what is all the set of all infinite paths generated by finite state transition systems are precisely those that can be expressed in this fashion. And this itself, what I've shown here, can be a specification language as well. Okay, and this is called omega regular languages. Language. Okay. So we will study that also, and you can have, and Buki automaton is exactly corresponds, it recognizes this set of omega regular languages. So when we talk later in the course, another course, Buki automaton, we might revisit this this thing. Okay, so that is something that I wanted to just mention, and in the context of the significance of why we want to identify SCC, because the strongly connected components, they represent the ways in which you can generate different forms of infinite suffixes in an infinite path in a finite state transition system. By the way, once again, as an aside, I don't think I will be spending, I'll only mention it now. LTL, as you know, the set of, they are path formulas, correct? So the set of LTL, any LTL formula represents, a set of infinite words, okay? The question is if LTL is equivalent to the set of words, infinite words, that, that any LTL formula represents. If the LTL, a class of LTL formulas, is it more expressive than, or is it equivalent to omega regular language? That is an interesting, question. It turns out that LTL is not as expressive as omega regular languages or Buki automaton, which the automata that recognize these kinds of infinite words. It turns out that LTL is less expressive. I mean, in the sense that the set of infinite patterns that it recognizes is less expressive than this. And that also is expressible in this fashion, but the restriction is that any infinite word that is generated by an LTL formula is restricted in the sense that you cannot have any arbitrary regular expression here in pi10 and pi11. You have to have something called star-free regular expression. Have you heard of star-free regular expression? Star-free regular languages? Was
No.
this?
Star free, is it related to the star in the?
Yeah, it is related to the star. So, yeah, but star freeness means you can't use like star, star like, in an arbitrary fashion in a thing. So a star-free language strictly is you can't have stars. But then, the only way you can have stars for is sigma star, okay? Or you can have the star operation. You can have all the complement, union thing, etc. that are allowed by regular languages. But there is you can use star only on sigma star. That is, if sigma is the alphabet, you can only use A plus B plus C plus D. Over the alphabet, or some star over the sigma, or some subset of sigma. That then you have all the other operations like concatenation and so on. So if you restrict yourself, that is the class of star-free regular languages. So if you restrict yourself in this infinite word pattern here, if you restrict the regular expressions pi10, pi11, etc., to star-free regular. You can go on Wikipedia and then check, okay, what a star-free language is. So if you restrict them, then that is exactly the class of LTL formulas. Okay, so but the moral is, what the key takeaway that we have to get from is LTL cannot express all properties of finite state transition, because it cannot express certain kinds of these kinds of omega regular properties. Of course, CTL star is more powerful, which you can do that in CTL star. Okay, but LTL, if you compare only LTL and omega regular languages, LTL is less powerful. Okay, so that's an aside. Okay, any questions here? Okay. Okay, good. So let me move on. So the labeling algorithm, just a quick recap. How do you start with EG of F1. So in both these labeling algorithms for EG as well as EU starts by assuming that you have already generated, you have labeled all the nodes in your transition system with the states corresponding to the sub-formula F1. Okay. Okay. Assuming that F1, then so then you prune the graph by keeping only those states which have F1 label. That is your starting point. Then you identify all the maximal strongly non-trivial maximal strongly connected component in that pruned subgraph of the graph for the original transition system. Okay, and so then, since any path on which paths EG of F1 should be an infinite path, every state of which has to be labeled with an F1 label. And so that's what we want to check. Since based on the observations that I made on the previous slide, every infinite path eventually will have a, will have to end up in a strongly, connected component. Okay. Therefore, since we have only retained, so if it has to, an infinite path will have to satisfy this EG, then every state in the strongly connected component will have to have the label F1, right? That's why you start by keeping only those states in which, which has those nodes which have label F1. Or if, there are no non-trivial components such in that pruned subgraph, of course, if that is empty, then, this EG of F1 is just false, okay? So, then if there is one or more SCC in that, then what you do is you take the union of all those states, okay? Union of all the states in each of the SCCs, and then you do a backward predecessor search. So you actually start, of course, you label all the states in that strongly connected component because they automatically satisfy EG of F1, correct? Okay, because the infinite paths generated by traversing the loops, the cycles inside the SCC, obviously they all have F1, so they all satisfy EG of F1. Okay, and then now you're only left with seeing if there is a tail, okay, a prefix tail that leads to from any state that leads and then ends up on this SCC, and that's what is checked here. Okay, the labeling of those states on this prefix is what is done here. So where you start from by picking a label there, and then you follow the predecessor chain, and then you label all of them with EG of F1 until you exhaust all the labels. Okay, so that's how it is done if you were using an explicit state algorithm. So is this clear? Any questions on this?
No, sir. It's clear.
Okay, good. So let me, so this we've already seen, since identifying SCC itself is of the same complexity as this one. And then after that, all you do is, finite, but arbitrarily long finite chains leading to the SCC. And so the overall complexity is the same as this. Okay, so let's quickly illustrate this using this example. Yeah. So this formula says that if all the paths from a state that satisfies start, okay, eventually from that every path will eventually so every path starting from a start, okay, once you press the start from start on every path, so eventually you will heat, you end up getting the microwave in a heat state. Okay, so that is true here because, as you can see, so the state that is this true for this thing?
No.
Yeah, it is not true because there are lots of paths here. So, for example, this is state 2 is not there, and therefore, when you do this algorithm, this should return false. Okay, so the first step is you convert them into into a form which has only the existential CTL operator. So EG is not of EF, and the negation of this, which itself, when you apply the negation to that, it is, a negation is implication. It is start and not of this, okay? So implication is a disjunction of not of start or this, and that is, and then you take the negation of the disjunction, it becomes a conjunction. So start and negation of AF of heat, and negation that is EG of not of heat. Okay, so that is the formula that you start with. So now you first label all the sub-formulas. So you start labeling all the the states with the proposition formula. So the states that get the label start is 2, 5, 6, and 7. 2, 5, 6, and 7. Okay. And the states where heat is false is all these states 1, 2, 3, 5, and also 6. Okay, because any state in which error is you can't heat. So first you start with that, and then you first have to compute the label all the this subformula, the states with this subformula. I'll compute the states that satisfy EG of not of heat. So this is EG. So how do you do that? Paramalai?
So, can you repeat the question?
Yeah. Now,
EG,
how do you simulate the algorithm for labeling EG, the formula EG on this thing? So what is the first step?
You take all the states which satisfy the not heat property.
Not heat, correct. Okay, so you keep only those states which have not of heat, which means you're throwing away 7 and
4.
And 4.
Yeah.
Okay, so this is gone. So when you remove that, then the second step is identifying all the maximal SCC. So if you remove these two states, then the only maximal SCC is this portion that contains 1, 2, 3, and 5, correct?
Yeah. 1, 2, 5, 3. That forms the cycle.
Yeah?
Yeah.
So,
and 6 can, okay, the 6 will not be a SCC. It doesn't even have a self loop.
which one? Yeah, there are 2.
6.
There's no self loop, okay, because that state is gone, no?
Yeah. I'm saying about 6. 6 will not be a SCC, right?
Yeah, 6. What did you say? So I didn't get it.
6 is not an SCC, right? Because it's a single node only, and it doesn't have
that
a
is not. So the SCC has just this one.
Yeah, 1, 2, 5.
Okay. So that is, so every state. So that is, every state in that is part of the SCC. Okay. Therefore, all those, 1, 2, 3, and 5 are the, all of them satisfied. Okay. EG of not of heat, correct?
Yes. Yeah.
Because, so that's the thing. You start by labeling everything by EG of heat because all the infinite paths, okay, paths are inside that SCC. So they all satisfy that. Okay. So that, and there is nothing that is, of course, you remove 4 and 5. Therefore, there's nothing that is going, there's no other state, okay, that is leading into that SCC, okay? So that, so the algorithm ends there, okay? So now then you have to compute the labels for this conjunction, okay? So, which is the taking the intersection of these two things. So that is 2 and 5. Okay. So this is the set of states that are labeled with start. This is a set of states labeled with the EEG, not a heap. And so you have the labels with two, because that's what you need for starting, for doing EF, okay? So now, so now we simulate the algorithm for EF. So you have 2, 5, and yeah. So you start with that, and then you start chasing the predecessors, okay? So what are the predecessors of 2? Okay, predecessors of 2 are 5 and 1. 5 already has, okay? Already has, see, EF is like, true until that, no? EF is EU of true until that thing, right? So technically, it's EF is E of true until this one, right? So you just any predecessor has to be included. So you will so you will include 1, okay, and then 1's predecessor is 4, and 4's predecessor is 7, 7's predecessor is 6. So you end up including everything, okay? And so because all of them end up because there is a path from each of those states that go and end up in this SCC, okay, which means every state in this satisfies EF of this one, okay? Is that clear?
Yes, sir.
Okay. Yes. So then when you take the negation, what you get is empty. And that's why there is no state that satisfies this, this thing. And therefore, this property does not hold for any state, and specifically the initial state, which is what we're doing. Okay. So that's how we do it. Okay. So if there are any questions, if there are any questions related to this, okay, then I will move on. So the next 2 things that I want to do today are extension of this explicit state algorithm to do fairness, okay, and then start introducing symbolic model checking method. Okay, so that's what I want to start doing. Yeah. Okay, so fairness. So once again, a recap of what is what is fairness. Okay, so a fair Kripke structure is one where you have added. So you want the ability to define fair paths, and that itself is defined, as I said, by defining a set of conditions. Okay, a set of predicates. Okay, called the fairness predicates. Okay, each of them a predicate means that it's predicates over the over S, which means they all denote some subset of the states. And a path is said to be fair if and only if every PI, if and only if one of the states in P1, one of the states in each of these, one of the states that satisfy that is in each of these things should occur infinitely often. Okay, so in a sense, it is fair. If so, which means anything that occurs infinitely often, a state can occur infinitely often on an infinite path in a finite state transition system, if and only if it is inside an SCC. Therefore, a fair, we first define a fair an SCC is fair if and only if one of, for each of these PIs, one of the states of PI is also is part of the SCC. Okay? And this should be true for every PI. Okay. So, do you understand? So, what this fairness requires is each of these predicates have to happen infinitely often, which in states parlance, what it means is that one of the states, it can be any one of the states that satisfies P1, has to be in that SCC. So the moment it is in SCC, it occurs infinitely often on any finite path. And this condition should hold good for every PI. That's when it is considered as fair. Okay, is this clear?
Yes, sir.
Yes, sir.
Okay. Yeah. So, I mean, now you kind of get an idea. See, I mean, as we've already observed in LTL, the fair, checking of a property under fair for the subset of fair paths is itself an LTL formula, so you don't need to do it in any special fashion. Whereas in CTL, you have to build it into the semantics itself before, and you have to make it as part of you modify the model checking algorithm itself in order to handle, in order to be able to check if these CTL formulas, but in order to restrict yourself to the subset of fair paths inside the Kripke structure. Therefore, that effectively means that you will have to change the notion of, you have to define what it means for in the semantics itself, what it means for a particular state to satisfy in a Kripke model, to satisfy a CTL formula in a under fairness assumption, and that's what I will be defining right now. Okay, so you recall that the standard semantics of CTL was this. Okay, where you define it in the standard function. Recall that Ex of F is true if there exists a path. If there exists a path starting from S such that in the next state, okay, in the next state on that path, F is true. So EG is true if it is true for every state on every. And there exists a path such that for all I, at every point in every state of that path satisfies the F. So similarly, for F until A2. So fair semantics is now defined, we use this, the F subscript for the turnstile. So MS of, this one satisfies under fair semantics. I mean, if it's a propositional label, there's nothing because there's no path to consider. Therefore, it is the same as before. If it is the formula of the form Ex of F, then we say that Ex of F satisfies is satisfied by the state in a Kripke model with fairness conditions, if and only if there exists a fair path from pi such that on that fair path, the next state satisfies F as per the fair semantics. Okay, so this is also recursively defined in the same way, but the important thing is that it requires that there exists a fair path. Okay, where the fair path is defined as something that I have that is already defined in the previous slide. Okay. Similarly, EG of F satisfies this under fairness condition, if there exists a fair path originating from S, such that every state on that path satisfies as per, recursively as per, as per the fair semantics. Okay. And this is also defined the same thing. So the only thing is that recursively you are defining it, using this. The critical difference, what exactly it looks like the same, you may ask, okay? The critical difference arises, after all, because all these, the case for EG and EU are defined recursively the same way. But the real difference comes from EX, okay? And the difference, here is the difference, okay? In fair semantics, EX of P may not hold in S. May not hold for a state S, even if P is true in the next state. Why? That is the critical difference. See, as per normal semantics, EX of P always holds for a state if there exists a path in which the next state holds, satisfies P. This is not true under fairness semantics. When is it not true?
If the path is not fair.
That is exactly right. There's no fair path. Okay, good. Yeah, so similarly, so that is one crucial difference. So EX of P just, even when the thing is, it may not. Okay, so there is this fairness thing that you will have to check, okay, as part of your semantics. Similarly, in fair semantics, AX of P can hold, in fair semantics, it is the dual. AX of P can hold in S, even if P is not true in any next state of S, okay? Why?
It is true by Waker's property. Every path can be not fair
because of the way the semantics of for all is done. Okay, so there are no fair paths at all. For all thing will vacuously become true, and this is why this is the crucial difference, which you will you will need to check when you do this recursive thing if every state, okay, in your recursive check if there exists a fair path or not, or if it is to ensure that you need to check, okay, that there exists a fair path in order to make this distinction. So that is the crucial difference, okay, because, and yes, okay, so that has to be can be handled only by changing the semantics, and then the algorithm then will have to explicitly, you will have to implement the fairness versions of these CTL operators. Okay, so that is the thing. So for example, to illustrate a little bit more, so let's take this example. The one that you've already seen. Suppose my fairness constraint has just one predicate, S1, S2. Okay. Does EF of X not P hold in S3? Paramalai? First,
No.
Why not?
Because EF demands that there exists at least a path. Yeah, EF demands there exists at least a fair path.
Correct. So there is no fair path.
It's not a fair path.
That is the critical thing. Okay. So from S3 there is no fair path at all. Of course, it will hold in S0, S1, and S2. Okay, because there are fair paths. Okay, that visit S1 and S2. I mean, either S1 or S2 infinitely often. Yeah. Okay, so you're right. So how about this, Amin? If my fairness constraint is S3,
No, right? Because like the first state from S naught itself is
That's
satisfying
right.
P.
I mean, the reason for that thing is the only, see, there is a fair path from S naught, correct? Which is,
Yeah, S naught, S1, S2, and S3, then S looping on S3.
yeah, if we loop in there, there is a fair path, but it so happens that
But it does not satisfy the
the,
EG.
yeah, the G condition, correct? Yeah. So whereas, for example, if you assume Q holds in states S0, S1, and S2, so EF, with the fairness constraint S3, EF Q until not P holds, okay? Because it does hold for S0, S0, S1, and S2, okay, all of them, because all of them have fair paths which end up in this thing, and in all of them, P is continuously true until, Q is continuously true until you reach not P. Okay? So you got the picture. Therefore, so with this, the modifications needed for the explicit model checking algorithm to do check CTL formulas under fairness condition is fairly simple. So check fair EG is the same as check EG. But you just have to restrict yourself to fair SCCs, okay? Because you need to check only for infinite paths on which, for fair paths, and the fair paths can be, the only fair paths possible, are ones in which end up in a fair SCC. So instead of including all the SCCs, you restrict yourself in the algorithm to only the subset of the maximal SCCs which are fair. Okay? Then, and that's all. And then you get check fair. And after that, you need to check, you need to do this. You need to add a fairness label, okay, that'll indicate whether in each state there is a fair path originating from that, okay? See, this can be done by doing EG of F of true, okay? Because true is obviously holds good in for every state. So EGF of true is true only if there exists a fair path, okay? Okay. So the states that satisfy this are exactly those states in which there is at least one path which is fair, okay? So you need to have this label. You need to have this information of whether there is a fair path from each of those states. Then check, the fair checking of EU formulas. EU formulas you can do by doing adding this label, conjoining this label to F2. Okay. So that's because you need to make sure when you're checking a F1 until F2, you have to make sure that the formula, because you start with F2 and then you check if there are paths leading to F2. But before doing that, you have to be sure that there exists at least one fair path from F2. Otherwise, because if it is an A kind of a formula, CTL formula there, then it can, if there is no fair path at all from state satisfy F2, then A kind of formulas can be trivially true there because of the semantic difference that I showed. And then, your EU check, will not be sound anymore. And therefore, you have to ensure that the state that satisfy F2 from that state is there exists a fair path. And therefore, and one way of doing it is to modify that label and make it stronger by making fair, using fair and F2. Yeah, and that's it. So you e.g. you do so that's it. So so let's is that any questions here?
No, sir.
Okay. So let's see application of that for this. So does EF of P until not P hold in S naught under the assumption not P? Obviously it holds, correct? That we already saw, because there is a fair path here, and Q until not P holds for that path. The fair path is something that goes from here and then keep repeating in S3. So how does this formula, this algorithm work for this? So first, you have to generate the label. So what are the fair states? Okay, what are the states that get a fair label here?
S3 will get fair.
Only S3?
I think every state will get the fair label.
Okay, what is fairness condition? So, the fair label you assign to a state if there exists a fair path.
Yeah, even from S0, S0, S1, S2.
Every state, is that
Yeah,
what you
yeah.
said? Every state, yes. So every state will get the label. So it is fine. Therefore, and then that you can check by doing EG of F true. So every state will get the fair label, and therefore it is the so S3 particularly is satisfies F, and then you do that. You do the thing. Okay. So what I will do is I will leave this as an exercise, okay, because I really want to finish. I will let you. Yourself. This is actually described in the book, so you can, try to do it yourself. This is mainly I want you to simulate, try to understand the, the change, that I just now described, by working this example out. Okay, so I will, leave it to you. So to try this example, and maybe other examples that you can construct, so that you will make sure you understand the algorithm correctly. Okay, so if there are no questions, then are there any questions so far? So this works the same way. So what you will have to do here is first, this is the fairness constraint, okay? The states that satisfy this. So first you will have to, EFG of not of heat. Anyway, so I will, if you kind of basically understand and you're able to do it, unless you have some very fundamental questions, I will take it, and otherwise I want to move on. Okay, any questions?
Sir, what is the fair strongly connected component? In a strongly connected component, if there is
fair, good. So that you did not understand then. See, a fair strongly connected component is there must be for each PI there must be at least one state that satisfies Pi
Okay.
among the states in the strongly connected component.
Okay. So essentially, the strongly connected component will have a path, will have a cyclic path which satisfies
And
every
then
one of
it
these.
will have a cyclic path.
Okay.
That, and therefore, on that, I mean, because the paths in SEC are cyclic, and since if there is at least one state has that, there will be at least one path in which that state will occur infinitely often. Okay.
Okay. So
That's what they're trying to ensure, because it is okay. So the fairness constraint requires that each predicate should occur infinitely often. Okay, which means that some state that satisfies each of this each of this predicate has to occur infinitely often. That's what it means. Sure. Yeah.
Okay, sir. Okay.
Correct. Yeah. For example, if you, I mean, in order to do EFG of knot of heat, what is your starting point? First, you label, the states that get knot of heat are 1, 2, 3, 5, and 6. Okay, and in order to start doing EFG, the first step is you keep only those states that have not heat. Okay, so effectively, you'll be removing states 4 and 7. In which not heat is not true. Okay, if you remove that, if you remove these two states, what is the only strongly connected component is this one on the left side, maximal strongly connected component. Correct? And you see that that is not fair as per this condition, because in all those states, this condition does not hold. Okay. So anyway, so that's what it is. So please do, simulate the algorithm and understand on this example before reading it in the book. Okay. And I might on assignment give you more examples to understand. Okay. So that's how that you do. Okay. So now I want to get started, at least the introduction part, with no, this I've already done. So, yeah, I mean, okay, so this is, okay, as a starting point, first I want to introduce reachability analysis using sets of states. Okay, so here we will be doing, we'll be looking at model checking algorithms where instead of using the graph and then analyzing the explicitly on the graph, we'll be using the symbolic representation for the transition relation and the initial state to do the analysis. Okay, as a first thing, I'm going to be illustrating to you, giving an idea of what how to do that. That's what I mean. Analysis using sets of states, or using predicates or formulas. Using predicates that are represented as symbolic formulas. You already saw how you could do, you could compute image, etc., symbolically, and that's what I'm doing here. Okay. See, one way to check AG of P. By the way, AG of P is an invariant property, correct? Because P is a predicate, not an arbitrary formula. Okay, that's what defines invariant predicate. Now, I mean, of course, AG of P you could check using arbitrary, treating it as an arbitrary CTF formula. But there is a quick one way to check is to, and this is what is called reachability analysis. Reachability analysis consists of accumulating all the states that are reachable from some set of initial states. Okay, pretty much what you're trying to do, reachability analysis on a transition system, is effectively consists of computing the transitive closure of R. Transitive closure R of T, the relation, okay, the binary relation, the smallest transitive closure that includes I. Okay, which means if S naught includes I, then it is included in R. If S is already in R, state in R, and S prime is a successor of TS, then S prime should be in R. Okay. Now, once you get, so this gets you all the states that are reachable from any set of initial states and no more. Okay, because it's the smallest transitive closure. So therefore, once you get that, then you can do EG of P, because EG of P, the invariant property requires that every state on every path originating from that state will have to satisfy P. So then what you do is you check if P is, if P holds true for every state. So that's one way of doing it. But this is, a technique that you can use to compute the set of all states that are reachable from any initial state by actually computing the image. Okay, so you start with image here. I mean, you already seen image, right? Image is image over a set is the set of things. So it is the image of some state. So you start by computing the image on the initial set of states. Then you can add that to your initial state and so on. Then you do image squared and so on until you exhaust. Okay, then until you don't add any new image states. Okay. At that point, you say that you have reached a fixed point for this transitive closure computation, and then that set that you have at the fixed point will have all the will include all the states that are reachable from any of the initial states in one or more more steps. Okay, for finite state systems, this has to terminate. Okay, and this is kind of the starting point for how you could do do model checking in symbolic fashion. Okay, now I want to make sure that you understand why this is symbolic. Okay, can you Amin, can you tell why I call this symbolic as opposed to the explicit state?
Like explicit state requires a graph, right? We need to
so here
check a graph, right?
That is one. You're not working on graph, it's one thing. But more importantly, although I have indicated these things as sets, okay, each set can be represented as, a set can always be represented by a propositional formula over the state variables, correct? And you know how to define image of X. We already saw that, no? How do you define image? Using existential quantification, correct?
So I'm not sure about the image thing.
Okay. So let's go to the next step. Okay. Now, image is, so here is what, I mean, although I'm using lots of things. So image is this one exactly. So ignore all the rest of things. So what is an image? This exactly represents this. Given a transition relation T, we already went through, you actually did. I thought there were some formulas, I mean, on your SAT. This is what I mean, okay? So image, X is, say, some predicate, okay, which denotes the set of states, okay? Image of X under that is exactly, X is a formula with state variable S. Then T is a formula over a pre-variable and a post-variable, SS prime. So you could, and this formula that I have in here is exactly represents what I call as image. So every state that satisfies this formula is something which is a successor state of some state that satisfies X. Correct? Because it says that it is true of those states S prime for which there exists a pre-state S which is inside X and which gets mapped to S prime.
Okay, now I get that, sir. We have seen this in the initial lectures.
What?
Now I remember that.
Yeah, okay.
We have seen this in the initial lectures.
Yeah, so it's in that sense that I say that this computes in a thing, because if you imagine that image is in each image 1, image 2, image 3, etc., they're all computing. So that is one, okay? And you notice another one, and this is kind of an indirect consequence. So since you're computing the formula that represents image 1 represents the the set of all states, okay, that in one step get mapped from some state inside the initial state. And therefore, what you're doing is you're kind of doing a more breadth-first accumulation of these states. That's why I have shown these arrows like this, okay? In one step, image is, getting you all the states that, get mapped from some state inside initial, and that you are unioning with the initial state. Therefore, this the second circle here includes every state that you can reach from S naught in one or fewer steps, where states that are reachable in 0 step I consider it as the initial state. So image square S naught union image S naught union S1, it gives you all the states that are reachable in 2 or fewer steps. And in each step, what you're doing is union, although I've said in here, union is like taking a disjunction, okay, on formulas, okay? The moment you get a formula representing S naught, then you take, which is, that or image of S naught, and so on, okay? It's in that sense that I call it a symbolic formula. And it's also the reason that here you don't need the graph, okay, but you need the symbolic representation of the transition relation and the initial states, that is as formulas. And then you are applying all these logical connectives. And to compute image, the most critical thing is you need the existential quantification operation as well. If you have all those things, then you can represent these things as a formula, okay? Of course, the formula will be in Boolean, okay? It will be a QBF formula because it involves existential quantification. Obviously, an existential quantification over propositional variables, you can always eliminate it. You can always convert them into proposition formulas. But, let's for the moment assume that we allow existential quantification in there. So in that sense, it is symbolic, okay? Now, another view of this thing. So I will do with this line, and then I will I will end. Okay. Another way to view, I've already kind of said it. So see this, you must have seen this kind of inductive definition, correct? Have you seen this kind of inductive relation definition in logic or any other course?
Yes, sir.
Yes.
Okay. Logic course in the first
And
semester.
the logic.
Yeah, good. So, and why do I say that it has to be smallest transitive closure that satisfies these relations? Because there are lots of trivial solutions for this. Give me a trivial solution that is not very interesting, okay? See, the set of all states obviously satisfies this, okay?
Yes, sir. Yeah.
Yeah, and you can see there are lots of other solutions for this. And that's why whenever you compute transitive closure, they keep saying smallest R that must include I, but that satisfies this thing. Okay, so that's the reason. That's why. And another way to view this thing is the reachability is as fixed points. Okay, you can view this way of computing or what it eventually produces as a fixed point x hat of some function. This is a higher order function. It maps a predicate, a set. See, whenever I talk about these things, I keep interchangeably using predicate or states, okay, set of states, okay? You should not. You should get used to it, okay? And then do not get confused, okay? So tau is higher order in that sense. It maps a predicate, a set of states, to a set of states, okay? I'm sorry. This should have been power set of S to power set of S, okay? Not S, power set of S to power set of S. Huh? Sorry, there's a mistake here, okay? So you can view this as a fixed point of a suitably defined higher order predicate, okay? That transforms one predicate to another, at which point it is tau of, it's a fixed point, okay? Of a higher order function, a predicate transformer is what I call. And what I get x hat itself is a predicate, a set of states. That is the least fixed point of this thing. So a tau, if I'm able to capture the transitive closure constraint using tau, then I can actually define it like like this. What I've shown here in picture here is one way of computing a fixed point, okay? And this happens to be a least fixed point in this case. Now, I think it is important for you to understand. See, this is fixed points, understanding fixed points and the theory of fixed points. I don't think I'll be able to cover the entire theory of fixed points. I'll give you bits and pieces. Is very crucially important for any branch of computer science, programming languages, and so on. I mean, I don't know if you have taken a course on lambda calculus. Have you?
Yeah, in the first semester I took.
Okay, so
Yeah,
they must have
for us
talked about
going
fixed
on
points
right
and so on, didn't they?
Yeah.
Okay, so that's good. Then I don't need to worry. So it can also
Actually,
be.
I only did the PLC course. The remaining two they are just taking now.
Okay.
This semester, so they are yet to cover that.
Yeah. So just remember. So we will look at this, and I think although you can understand this whole thing, in an algorithmic way, I think it is important to view it this way because there is such a rich theory behind fixed points of these functions that any algorithm that you can devise, if you view them as computing some fixed point of some appropriate higher order function, proving the correctness of those things, you can then rely on the all the infrastructure, the theoretical framework that the fixed point theory gives you. Okay. So, for example, there is this famous theorem due to Kleene and Tarski. Okay. Sometimes, by the way, that least fixed point is denoted this way. Okay, of a particular higher order predicate is defined. Okay, is denoted this way in a like Z. Okay. See, there is this famous Kleene-Tarski theorem. Okay, says that if tau, this higher order predicate, is monotonic, then you may wonder why should fixed points exist at all for any predicate, and why should it be unique, and all kinds of questions. Okay, here it is quite clear because you keep on accumulating. In finite state systems, eventually you reach a limit point, which is what I call as a fixed point, and that is actually the least fixed point here, because of the way that you're computing. And the theorem that really guarantees existence of fixed point, uniqueness of fixed points, and the way that is computed here is due to Kleene and Tarski. Okay, now I'm going to be covering Kleene and Tarski a little bit later in the course, but first I want to cover all the intuitive thing and the algorithm so that you can get started on this project using BDD. Okay, so the Tarski theorem says that tau is monotonic, that this least fixed point indeed is guaranteed to exist and is also unique. Okay, and furthermore, it says that fixed point can be computed as the limit of an infinite chain starting from false. Okay. Now, you see, tau is a predicate transformer. It takes a set of states and then maps it to another set of states. Therefore, you can false is the empty set, and therefore you can apply tau repeatedly to the previous thing. So, and what Kleene and Tarski theorem states is that if tau is monotonic, tau is monotonic and the domain is finite, then for some finite I greater than or equal to 0. I mean, this theorem holds good for infinite system as well, but you may not be able to compute this way of computing as a limit of ascending chain. That procedure may not terminate for infinite state system, but for finite state systems, this is one way to compute it. Okay? This is a very fundamental theorem in logic as applied to programming logic, because you can express all the semantics of programming languages and programs, etc., as fixed points, and you could use this theorem to compute those fixed points. For example, while programs are exactly do this. Okay. Now here is what I've shown as a generic way of writing a program that does this. It's a general scheme to compute the least fixed point. Okay, given a predicate transformer tau. So it uses this Kleene-Tarski theorem to repeatedly compute this chain, tau chain, okay, starting from false. So it initializes tau q prime to tau of q for some appropriately defined tau. Okay, so then that's what it's doing here. So each time it is applying a new instance of tau to q prime, and then you're doing it. Okay. Now, for example, so the one that the specific computation of this accumulating this image here on the left side can be expressed as in terms of an appropriate tau. Okay. So I'm asking the question: what is a suitable tau to implement reach in this fashion that I have done here? Okay. So that's exactly this here. Here it is. Okay. So it's exactly describes it, the tau, in a symbolic fashion of what is being done in each step. Tau represents the predicate transformation that happens in each step of this fixed point computation. Tau fx is I. You're taking the initial state and unioning, that is taking the disjunction of that and computing. Yeah, you're adding I to it and applying it to some x. Given an x, that's what it does. It does compute the image of x and then unions that with I, where the image is as I indicated. Now, when you apply this tau to starting from false, that is the ith iteration of tau I of false, which is what is being done here. This is what you get. Okay, so you're starting with false. Each time you are unioning I with false the first time. Tau 0 is false. Tau 1 is I union false. Then tau 2, which is tau 2 of false, is tau 1 of false, which is I or image of I. Then you have things like this. The third step, you have I union image of I union image of I. Image of I union image of I, and so on. Okay. And if you expand this thing out, what it really, this is equivalent to I union image of I union image squared of I union blah blah. Okay. That's exactly what you're doing, and you're doing this until you reach a fixed point, a point at which the I+1 application of tau is equal to the same as the thing. So that is the fixed point of tau. The reason that it is I mean, I've already given you a reason why it is important to understand it as as fixed point. Okay, this computation, what you're doing here is a fixed point of tau. That's because, and furthermore, okay, you will see in the next class that all CTL model checking, you can actually, what we did there in explicit state model checking, every CTL operator, the formula that it represents for every CTL operator can be defined as fixed points of a suitably defined tau, a predicate transform. Okay, so I will stop here, and if you have any questions, you may ask. Any questions?
No, sir.
Okay, good. So I'll see. Oh, by the way, there will be a BDD tutorial. Okay, the first two classes, one Saturday, one Monday. Okay, that is, I think it's very critical for you to understand, because I'm sending out the second assignment pretty soon. Okay, and then I want you to start. So this part will have two parts. This project, the first part will require you to implement a CTL model checker, which I'm starting to describe, and I will complete it in next time, in the next class, using BDDs. Okay, BDD is just a representation of propositional formulas. You can actually represent them as a CNF and then use a SAT solver. But of course, you will have to do existential quantification elimination, which is kind of expensive when you stick to CNF-like formula. So you have two choices if you want to use SAT solver. You can use QBF, okay? But we're not covered QBF. Or you could use BDDs, and then the existential quantification elimination is quite efficient when you're able to represent all your formulas that you generate along the way as BDD. That's a canonical representation. And that's what will be covered by Diganta on Saturday at 5:30 and Monday at 5:30. Okay, so that Monday he will be actually demonstrating how you use the CUDD package, the BDD package. So I suggest that you attend those things. The first part will be implementing CTL model checker, without fairness, and the second part will be with fairness. Okay, for the second part, I want each of you to do the implementation separately. But for the second part, I don't mind if you collaborate, okay? But each of you will have to get an implementation of your own on this project, okay? On this first programming project. So it is crucial that you attend and you cooperate with me and attend the two special tutorial sections. And the Zoom link that you have to use is the same as the same as for the regular course, okay? And so it's tomorrow at 5:30 and on Monday at 5:30. Okay.
So we will be implementing with the second algorithm using fixed points.
Everything will be implemented using C. Yeah, yeah. Okay. No. The explicit state algorithm was just to see. So sometimes people are more comfortable. They understand when you do things in a graph theoretical way. This fixed point computation, in terms of a symbolic computation, sometimes it's a little bit puzzling, a bit mysterious, okay? And that's why I usually cover that after that. Yeah. Answer to your question, a short answer to your question is you'll only be implementing symbolic model checker, not explicit state, that too using fixed point computation, okay? Because you could do that once you understand the fixed point semantics and the fixed point semantics of CTL operators, you can do it fairly quickly. But that requires you to get acquainted with BDD packaging. Yeah.
Okay, sir. Sir, also these model checking algorithms are not like the one in Z3, right? Because in Z3, only specific instances of the problem will be solved, and for other instances, it may not solve.
No. So don't get confused. Okay. See, you can have no. Okay. Z3 SAT solver. Z3 has lots of. It's a very, very powerful theorem prover. What you saw was just the SAT solving part of Z3. Okay. You could, as you saw, you could, type in quantified Boolean formulas. Okay. There is a fixed point engine. Okay. All the examples that you saw, you're right, that you were able to only kind of generate some finite propositional formula, even if it is in QBF form, and all the examples for the games, etc., involved in, expresses satisfiability. Okay. Now Z3 also has a fixed point engine. Okay. It's a fairly advanced fixed point engine. It can compute fixed points of, recursive equations. Okay. You can have recursive equations like these, transitive closure like thing. Like I said, oh, I have a tau. I'll define a tau. Give me an x hat, exactly like what I said here. Okay. You could pose to Z3 things like this.
Okay, for any recursive function, it will compute. It will
Well. Okay. There are some restrictions. Okay.
Okay.
So, for example, if it's your finite, domain, and you have actually, it may work even some extensions. At least the propositional part of it, assuming that they're all finite. So it can give you the mu. Okay. It can actually give you the x hat. Okay, as a symbolic formula.
Okay.
And then, that they will be ugly. You rarely want to print that thing out. But then you can ask, oh, does my fixed point then satisfy? Does it satisfy certain property? For example, after computing this fixed point here, what is it that you want to check in order to do model checking? You have to check if the initial state is included in that, correct?
Yeah.
Now, for that, you don't need to view the fixed point. You can actually use the fixed point engine of Z3, get the fixed point, and then check a Boolean property about that. Okay, that you can do in Z3. So that is the fixed point engine of Z3 is a model checker. Okay, it's pretty much a symbolic model checker. So there is an engine in there. Okay. So Z3 is more than just doing satisfiability checks. Yeah.
Yeah. Okay.
And actually, in this course, we'll be covering. See, those are the kinds of things that I want to cover in this course, and do less of an emphasis on Buki automata, omega regular languages, because there are other courses that you can take. So there is something, the thing called PDR, property directed reachability, and that's what is called as IC3 if you look at the thing. So I will be covering, towards the end. So they are very advanced versions of model checking. Okay, what I'm covering right now is some more like what is used in USMV and so on. Okay. Yeah.
Yeah. Okay, sir.
Okay, that's a good question. Thank you.